Let me ask you something that sounds almost too simple to bother with. When you open your freezer and that wave of chilly air hits your face, what exactly is coming out? What is that stuff we call cold? It feels like something, right? It sneaks into your sleeves, bites your fingers, makes you hunch your shoulders like the air has tiny teeth. We talk about it like it's a substance. We say, close the door, you're letting the cold in. We blame the cold for stiff joints, foggy breath, and the general injustice of winter mornings. Cold, in our everyday language, behaves like a thing. A sneaky, unpleasant, invisible thing. But here's the strange part: physics looks at all that dramatic shivering and says very calmly, cold doesn't exist. Now that sounds like the kind of statement designed to annoy people. You're standing in the snow, your ears feel like they're about to snap off, and some physicist strolls by and says, actually, what you're feeling isn't cold. That's the sort of moment where science risks getting punched in the nose. So let's not be annoying about it. Let's be curious instead. Imagine you're holding a hot mug of coffee. You wrap your hands around it and go, what are you really feeling? We say heat. But what's happening physically is that energy is moving. The mug is warmer than your hands, so energy flows from the coffee into your skin. Your nerves are sensitive little devils. They detect that energy transfer and send signals to your brain, which helpfully translates all that microscopic hustle into the cozy feeling we call warmth. Now switch the scene. You put your bare hand on a metal railing outside in winter. Yikes. That's cold. But what's actually happening is cold flowing from the railing into your hand the way heat flowed from the coffee. Here's the twist: no. The energy is going the other way. Your hand is warmer than the railing, so energy flows out of your hand and into the metal. Your nerves don't carry little thermometers. They're mostly sensing the rate and direction of energy flow. Rapid energy leaving your skin feels like cold. Rapid energy entering feels like hot. So in both cases, the mug and the railing, there's only one real physical stuff being traded: energy. Heat is energy in transit due to a temperature difference. But cold, that's just our name for the absence of heat, or more precisely, for heat leaving us. It's a bit like money in a bank account. Suppose you check your balance and see you have less money than yesterday. Do we say that poverty flowed into your account overnight? No, money flowed out. Poverty isn't a thing that comes in bags and gets dumped on you. It's a lack of money. Cold is like that. It's not a substance sneaking around the universe. It's what we call a situation where there's less thermal energy around, or where energy is leaving you. But the story gets even more interesting when you zoom in to the microscopic level, because that's where physics really earns its keep. Everything around you, the air, your skin, the chair you're sitting on, is made of atoms and molecules. And those little guys are never still. Even in a solid where things look calm and rigid, atoms are jiggling in place like people stuck in their seats at a concert, dancing as much as they can without bumping too far into their neighbors. In liquids and gases, they roam around more freely, bumping and bouncing like hyperactive bumper cars. Temperature, at its core, is a measure of how energetically all that jiggling and bouncing is happening. Hotter means faster, wilder motion on average. Colder means slower motion. Not no motion, just less. So when you say something is cold, what you really mean is the atoms and molecules in that thing are, on average, moving more slowly than the ones in you. When you touch it, you're faster. Moving molecules crash into it slower, moving ones, and share some of their energy. Your molecules slow down a bit, they speed up a bit. You experience that loss as the sensation of cold. Notice what's missing from this picture. There is no cold particle. No little blue specks labeled cold flying from the ice cube into your finger. There's only motion and changes in motion. Heat has a very clear physical identity, energy being transferred because of a temperature difference. Cold is just our poetic way of describing a direction of that transfer and a relative lack of motion. And this leads to a deliciously weird idea. If cold is just less molecular motion, could we, in principle, keep removing motion forever? Could we make something so cold that its atoms stop completely? Physicists have a name for the lower limit of temperature, absolute zero. That's the point where molecular motion is as low as the laws of quantum mechanics will allow. You can get closer and closer, but you can't quite reach perfect stillness. Nature doesn't like complete silence at the atomic scale. There's always a faint jitter, a kind of restless whisper built into reality itself. So the coldest possible thing in the universe is not full of coldness. It's just a place where motion is minimized as much as the rules permit. Still no cold substance, just less and less jiggling. Already, the everyday picture starts to wobble. We walk around talking about hot and cold like they're equal opposites, like light and dark or up and down. but physically, they're not symmetrical at all. Heat has a concrete meaning in terms of energy transfer. Cold is what we say when that transfer goes the other way, or when there's less energy around to begin with. That's a pretty radical shift hiding inside a very ordinary word. And once you start looking at the world this way in terms of motion, energy, and the invisible dance of atoms, all sorts of familiar experiences start to look a little suspicious, like they've been oversimplified by our senses. And that's where the real fun begins. Want me to keep going? Good, because this is where the everyday world starts to feel like a magic trick once you know where to look. Think about this: you walk barefoot across a room. First you step on a rug. Feels fine. Then you step on a tile floor. You jump like you just stepped on a block of ice. But here's the puzzle: the rug and the tile have been sitting in the same room all day. Same air, same thermostat, same everything. A thermometer would tell you they are at the same temperature. So why does one feel warmer than the other? If cold were really a substance, you'd have to say the tile somehow has more cold in it than the rug does. But that falls apart immediately, because leave them there long enough and they're in thermal equilibrium. That's a fancy way of saying they've settled into the same average molecular motion. The trick is not about how much energy they have, but how fast they can move energy around. Tile, stone, metal. These materials are like superhighways for energy. Their atoms are arranged in ways that let vibrational energy zip through them efficiently. So when your warm foot touches the tile, energy drains out of your skin quickly. Your nerves scream, "Whoa! Energy leaving fast!" And your brain labels that sensation cold. The rug is more like a traffic jam. It's full of air pockets and tangled fibers that are terrible at conducting energy. When your foot touches it, energy still flows out. It has to if there's a temperature difference. But it trickles instead of rushes. Your nerves say, "Not much happening," and you interpret that as warm, or at least not cold. So the sensation of cold has as much to do with rate as with temperature. Your body is less of a thermometer and more of a flow meter. It's measuring energy traffic, not just energy level. Here's another fun one. Take a piece of metal and a piece of wood and put them both in an oven at, say, 350 degrees Fahrenheit. Let them sit there long enough to be absolutely, unquestionably the same temperature. Now, very foolishly, touch them both. They will both burn you, of course. Please don't actually do this unless you have a strange desire to learn physics the painful way. But the metal will burn you faster and more severely. Why? Because now energy is rushing into your skin, and the metal is extremely good at delivering it in a hurry, same temperature. Completely different experience. Our language of hot and cold blurs together temperature, energy, and energy transfer in a big conceptual stew, and our nerves are just reporting local traffic conditions. Once you start thinking this way, you can reinterpret all kinds of ordinary things. Ever notice how a draft in a room can make you feel cold even if the air isn't that chilly? Moving air carries energy away from your skin more efficiently than still air. It's not that extra cold is blowing on you, it's that the conveyor belt carrying your body's energy away just sped up. This is also why blowing on hot soup cools it down. You're not blowing cold into the soup. You're helping energetic molecules escape and be replaced by cooler air, increasing the rate at which energy leaves the liquid. Again, it's all about motion and transfer, not some ghostly cold fluid. People used to think there was a fluid, by the way. In the 18th century, scientists had a theory of heat as an invisible substance called caloric. Hot objects had more caloric, cold objects had less. It was a neat idea, tidy and intuitive. You could imagine caloric flowing from one place to another like water. The problem is, nature didn't cooperate. Experiments started piling up that didn't make sense if heat were a conserved fluid. One of my favorites involves boring cannons, yes, artillery, the kind that goes boom. When metal cannons were being drilled out, the boring process produced enormous amounts of heat, seemingly without limit, just from mechanical work. If heat were a substance stored in the metal, you'd expect it to run out at some point. But as long as you kept doing work, pushing, grinding, stirring at the microscopic level, more heat appeared. The conclusion was shocking at the time: heat isn't a material fluid at all. It's motion. Mechanical work can be converted into microscopic jiggling of atoms, which we experience as a rise in temperature. That was one of the big clues that led to the modern understanding of energy conservation and thermodynamics. And once you accept that heat is motion, cold becomes even more clearly a bookkeeping term, not a physical ingredient. Let me give you a picture I like. Imagine a gigantic dance floor filled wall to wall with people. They're all dancing, but at different levels of enthusiasm. In one corner, the music is wild and everyone's jumping, spinning, waving their arms. In another corner, it's a slow song and people are just swaying gently. Now remove the imaginary walls between those corners. The energetic dancers bump into the slow dancers. Some of their excitement spreads. The wild crowd calms down a bit. The sleepy crowd livens up. Eventually, everyone's moving with about the same average energy. That's temperature equalizing. That's heat flow. Nobody ever pours slowness into the fast dancers. There's only ever transfer of motion from more energetic to less energetic people. Cold, in this analogy, would just mean the part of the floor where people are moving less on average. It's a description of a state, not a thing you can scoop up in a bucket. And yet our language keeps trying to turn it into a thing. We say, cold is coming in through the window. But what's really happening is that energy from inside the house is flowing out through the glass to the colder outside air. The direction of energy flow is outward. We just experience it from the inside and blame the invading cold. This reversal in perspective is one of the most useful habits you can build in physics. Whenever you think something is coming in, ask whether something else might actually be going out. Often, the universe is running the same simple rules, and our brains are the ones telling the backward story because that's how it feels locally. Now here's where it gets even more interesting. Temperature, which seems so straightforward, just a number on a thermometer, is really a statistical story. It's about averages over mind-boggling numbers of particles. Any single molecule in the air can be moving faster or slower than the average. Temperature doesn't tell you what one molecule is doing, it tells you about the crowd. So when you say something is colder, you mean the average kinetic energy, the average motion of its particles is lower. But averages can hide a lot of detail. Even in very cold air, there are always some speedy molecules zipping around. And in very hot air, there are always some sluggish ones. Nature is messy and democratic like that. All of this builds toward a slightly unsettling realization. Our sensory categories, hot, cold, warm, chilly, are not fundamental features of the universe. They're human interpretations of energy exchange between our bodies and our surroundings. They're real experiences, absolutely, but the labels we slap on them are part of a translation layer between microscopic physics and human survival. We evolved to care about whether we're losing heat too fast or gaining it too fast, because either extreme can kill us. So our nervous system developed alarms for energy flow, not for abstract quantities like average molecular kinetic energy. Physics comes along later and says, okay, let's clean up the language and figure out what's actually moving around down there. And when we do that cleaning, cold quietly disappears as a physical entity. In its place, we get a simpler, more universal idea: energy spreading out, motion being shared, differences evening out over time. But that simple idea has some very deep consequences, especially when you start asking why energy always seems to spread out in one direction and not the other, and what that has to do with the way time itself seems to flow from past to future. All right, now we're really in the good stuff, because once you start talking about energy spreading out, you're only one small step away from one of the deepest ideas in all of physics. Why the future is different from the past. Let's go back to our dancing atoms. You've got a hot object, atoms jiggling like crazy, and a cold object, atoms barely wiggling. You put them in contact. What happens? The energetic atoms bump into the sluggish ones and share their motion. After a while, everything settles into a common middle ground. You never see the reverse. You never see a lukewarm cup of coffee sitting on a table suddenly separate itself into a hot top half and an icy bottom half with no help from you. The laws that govern individual atoms, the basic mechanics of collisions and forces, don't actually forbid that kind of rearrangement. If you ran all the molecular motions backward, it would look perfectly legal. But in practice, it just doesn't happen. Why? Because there are vastly more ways for energy to be spread out evenly than for it to be clumped up unevenly. Imagine you have 1,000 coins and you dump them on a table. How many ways are there for them to land in a neat stack, one exactly on top of the other? Practically none. How many ways are there for them to be scattered all over the table in a messy pile? An astronomical number. Messy is overwhelmingly more probable than neat. Temperature differences are like neat stacks. A hot object next to a cold one is a special, organized situation. Energy is concentrated here, sparse there. Once you let atoms collide and exchange energy randomly, the system wanders into one of the enormously many, mixed-up states where energy is more evenly shared. That's what we call thermal equilibrium. This tendency has a name: entropy. It's a measure of how many microscopic arrangements correspond to the same overall macroscopic appearance. High entropy means there are tons of ways to realize that state microscopically. Low entropy means there are only a few. A hot object next to a cold one is relatively low entropy, special structured. Uneven. Two lukewarm objects at the same temperature is higher entropy, more uniform, more ways to arrange all those molecular motions without changing the overall picture. So when heat flows from hot to cold, entropy increases. Energy spreads out into more probable arrangements. And that one-way tendency from less probable to more probable is what gives us the arrow of time in everyday life. Now here's the wild connection. When you say something gets colder, what you're really describing is energy leaving that thing and spreading out into its surroundings, contributing to this grand march toward higher entropy. Cold is not a substance being added, it's a local sign that energy is dispersing into the wider universe. Your cup of coffee cools down not because cold sneaks in from the air, but because the coffee's energy spreads out into the air molecules, the table, the room, and ultimately, in a very tiny way, the rest of the universe. The coffee's atoms jiggle less on average, while everything else jiggles a bit more. The total energy is conserved, but it's more evenly smeared out. And once it's smeared out, it's incredibly unlikely to spontaneously gather itself back into your cup in just the right way to reheat your drink. Not impossible according to the microscopic laws, just so absurdly improbable that you'll be waiting longer than the age of the universe with your mug in hand. So the reason cold seems to take over is tied to the same reason eggs don't unscramble and smoke doesn't leap back into a cigarette. It's all about probability, about the number of ways atoms can arrange their motion. This gives a funny twist to our original claim. Cold doesn't exist as a physical thing, but the processes we associate with cold, cooling, energy loss, slowing motion, are deeply woven into the statistical structure of reality and the direction we experience time. When you feel a winter wind on your face, what you're sensing is your body's organized, high-energy molecular motion being gently randomized into the vast, colder environment. You are, in a very literal sense, participating in the universe's drive toward higher entropy. Cozy, right? But here's something even more delightful. Our very ability to think, to remember the past and not the future, is connected to this same one-way flow. Memory formation in your brain involves physical processes, chemical changes, electrical signals, tiny rearrangements of matter. Those processes increase entropy overall. The arrow of time that lets heat flow from hot to cold is the same arrow that lets causes precede effects and memories point backward, not forward. So when you say, I remember when the coffee was hot and now it's cold, you're using a brain that only works because of the same thermodynamic asymmetry that cooled the coffee in the first place. And in that big picture sense, cold is not an enemy or an intruder. It's a signpost. It's telling you that energy differences are smoothing out, that the universe is exploring more and more of its possible microscopic configurations. That time, as we experience it, is moving along. From the viewpoint of the atoms, nothing dramatic is happening. They're just colliding, exchanging energy according to simple rules. No atom ever says, I shall now deliver some cold to this human. There's only motion being shared, but from our human scale, built to notice imbalances that matter for survival, those tiny exchanges add up to wind chill, frostbite, comfort, and the pleasure of a warm blanket. We live in the gradients, the differences in temperature, pressure, energy, because that's where interesting things happen. Where there are differences, there can be flows, and where there are flows, there can be life. If everything were at exactly the same temperature everywhere, perfectly uniform, perfectly equilibrated, nothing much would happen. No weather, no engines, no metabolism, no thinking. The universe would be in a kind of dull thermal haze. The very fact that you can complain about the cold means the cosmos is still gloriously out of balance in places. So the next time you step outside and say, wow, it's cold, you can smile at the hidden story. There's no mysterious cold stuff attacking you. There are just countless microscopic collisions, redistributing energy, nudging the world toward equilibrium one jittery atom at a time. And somehow, out of all that blind jostling, emerges not only temperature and time, but creatures like us who can stand in the wind, pull our coats tighter, and wonder what it all means.